So example 3, page 3. So let's remember the real system. We've got our truss coming out like there, coming down like there, and then going up like there. And remember that we have a 90 kilonewton load there, and we've also got a 90 kilonewton load there. And then of course these two ends are pinned. So when the structure deflects, we could expect a deflection like there on the exaggerated scale. So we can see that the end of the truss has deflected a distance downwards, and it's quite reasonable to assume that there's a horizontal deflection to the left. So we would expect the truss to move downwards under that load, and we would also expect the truss to move to the left. So if we wanted to calculate this horizontal deflection to the left, what do? We apply a unit force, and that unit force let's call the horizontal deflection to the left, that value there. We apply a unit force, so that unit force, we'll just call it 1 bar, or the horizontal force, to the left or to the right, and that would then become equal to the sum of all of the n bar ends over EAs. And we'll take up the L for that being all members. So if we wanted to test to make sure that the direction is correct, why not apply this horizontal unit force to the right, and we would expect that it would turn out to be negative. So as before, draw out the truss. So we'll have our truss like there, and we want to work out the horizontal deflection under we want to work out the horizontal deflection. So at the end of it, let's apply a unit force of 1. Now if we want it to be dimensionally correct, you might want to have those as kilonewtons, and then therefore that side as kilonewtons. So when you did that calculation, the delta would turn out to be in millimeters, since delta would be equal to the sum of the n bar n L's over EA divided by this 1 bar, or the 1 bar that you've applied to the left to the right in terms of kilonewtons. So let's work out the force in tension. So the whole of the bottom chord is obviously going to be in tension. So let's draw the tension there, and then we will stick. We will just solve that to say on that member there's going to be a tension force of 1 kilonewton, and then on that member there's going to be a tension force also of 1 kilonewton. So let's list out our members as we did before. So member 1, 2, 3, 4, 5, 6. Let's stick in the lengths in terms of meters. So we'll call that 8, we'll call that 5, 5, 5, 4, and 8. Our EAs. Now E is equal to 200 times 10 to the 6 kPa, which is equal to 200 times 10 to the 6 times 10 to the 3 newtons per meter squared equals 200 times 10 to the 6 kilonewtons per meter squared, with kilonewtons being our base unit, and that's obviously equal to 2 times 10 to the 6, 10 to the 8 kilonewtons per meter squared. Therefore we have A, which is A is equal to 0.0008 meters squared, and the product EA is going to be equal to 1.6 times 10 to the 5 kilonewtons. So let's just not do a shortcut like we did last time, and we'll just say that the EA is all going to be in units of kilonewtons, and the value is going to be 1.6 times 10 to the 5 kilonewtons. So we can put in our n. So remember that our n, or this n there, is from the real system. So this is the real system. So it's just the same as the values that we had before, but let's just limit ourselves down to this minus 480 in terms of kilonewtons, and also the minus 120 in terms of kilonewtons. Now we've got this unit force N in kilonewtons, or the N bars for the virtual system, and remember that there's no deflection associated with the virtual system. So down here we've got 1 in tension, and we've also got 1 kilonewton in tension, and all of these other values are 0. So we work out the product. The product is N multiplied by N bar multiplied by L divided by EA, and if we want it to be really pedantic, which we weren't last time, let's just divide it by this 1 kilonewton, or this 1 kilonewton there, because we expect a deflection to be out of it. So let's just divide this by 1 kilonewton, which represents the virtual the virtual force, and you can see it's 1, so it's all unity. So we do that calculation there, and we end up with 120, or negative 120 times 1 times 8 for the meters. Divide that by EA, which is 1.6 times 10 to the 5, and divide that by 1 kilonewton, and we will end up with an answer in meters, because that would be the units of negative 6 times 10 to the 3, sorry, 10 to the minus 3 meters. So the units, the units of all of that turns out to be meters. Okay. And on this side here we've got the 480 multiplied again by 1, divide that by EA, and divide that by the 1 kilonewton force that we've applied, and we'll get a value of minus 12 times 10 to the minus 3, all in meters. So the sum of those two values is going to be the negative of 18. It's going to be the negative of 18 times 10 to the minus 3 meters. And if we wanted to convert that into millimeters, we get that will be negative 18 times 10 to the minus 3 times meters is equal to minus 18 millimeters. So the horizontal deflection delta that we've calculated is negative 18 millimeters, and that implies that the horizontal deflection is in the opposite direction to the 1 kilonewton or to the 1 bar that we've applied, and that can be expected from the reasons that we talked about at the start. So we can indeed see that the horizontal deflection has gone to the left by 18 millimeters. So let's have a look at the other numbers. Well, that's 240, that's 150, that's 300, and that's minus 150. So we can see that 240 times 0 is 0, 150 times 0 is 0, 300 times 0 is 0, and minus 150 times 0 is 0, which is why we didn't really need to do that bit of the calculation, and we could have just considered members 5 to 6 in terms of this calculation. So so the quicker way to do it would just be to consider members 5 to 6 and just ignore the rest of the members, and then see what work is done on that side against the real forces. Note that the real force is negative or in compression, and the virtual force is in tension, which is why we get a negative value on those sides there. Now, if you had the virtual force of 1 kilonewton acting to the left instead, the overall answer would have turned out to be positive, because the two values would have cancelled each other out in terms of negative times negative, which would have led to a positive. And since that force is acting to the left, you would expect that to be, well, that was acting to the left by 18 millimeters.